Everyone, hello. We're going to start the next session. My name is Sylvain Baillet. I'm based at McGill in Montreal, and I have the pleasure to co-chair this session this morning on novel imaging acquisition methods with Dr. Joseph Culver. We're going to get started immediately with the first presenter, Aahana Bajracharya. I'm sorry if I mispronounce your name. Very sorry about it. And the title is Developing Methods for Precision High-Density Diffuse Optical Tomography. Please.
Can you all hear me okay? All right. Hello, everyone. My name is Aahana Bajracharya. I am a PhD candidate in imaging science at Washington University in St. Louis. And I will be presenting my project on developing methods for precision high-density diffuse optical tomography. I have no disclosures. So let's start with some background on the technology behind diffuse optical tomography. As we all know that from the fMRI literature, neuronal activity is an energy-consuming process that causes changes in oxygenation of hemoglobin in the blood. Conveniently, hemoglobin is also a chromophore, that is, it absorbs light, and this absorption differs depending on the oxygenation level. Functional near-infrared spectroscopy has long taken advantage of this property to draw insightful conclusions about cortical hemodynamics. When we shine near-infrared light to the surface of the scalp, it follows a curved trajectory given the absorption and scattering properties of different types of tissues in the brain. However, to map brain function effectively, we require more than one source detector pair. High-density diffuse optical tomography uses a dense array of regularly spaced sources and detectors to measure the underlying brain activity with better lateral resolution and depth profile. Now, going back to fMRI. As we all know, functional MRI is the most common method of brain mapping, and it has helped establish foundation of a large body of literature that has informed novel image acquisition methods. However, despite the tremendous strengths, the physical limitations posed by this device makes it difficult to carry out experiments that are close to the real world. Children and older adults in particular have a hard time undergoing long durations of scan in the scanner. This is where HDDOT can help complement fMRI and fill the gap. HDDOT is an imaging modality where you are able to be scanned in a more ergonomic manner while seated on a chair, are able to have a conversation with another individual, and also be moving around. We have a lot of posters from our group demonstrating all of these projects, so please do check them out later. So here's also a video of one of our newest systems where a participant is freely moving with the imaging cap on their head. And all of these features of HDDOT helps expand the possibilities of non-invasive functional neuroimaging of the brain. Prior work from our lab has shown the capability of HDDOT as a viable surrogate for MRI. And this video of functional brain activity over time while the participant watched a flashing checkerboard, a rotating checkerboard across both imaging modalities demonstrates the fact that it could be a viable surrogate. And over the years, work in our lab and across many others have made tremendous contributions in the field of functional near-infrared spectroscopy to be a valuable research to the neuroscience community. So why not take this a little bit further? Neuroimaging studies have traditionally approached data reliability through the lens of large and consortium-type studies. However, in recent years, precision-focused studies with small number of individuals have been gaining popularity. So the fMRI literature in the last decade has shown incredible amount of detail that we are able to learn from individual level studies. And given the trajectory that neuroimaging research in general is headed towards, it is promising to see where precision studies can, where they go and where optical neuroimaging type precision studies can also be more informative in that manner. So although well established in fMRI, it is a novel concept in HDDOT. So the goal of this project is to investigate the feasibility of doing precision functional MRI, functional mappings using DOT. So given the novelty of this idea in DOT, we have additional considerations while designing standard operating procedures and during data collection and analysis. So during data collection, we place our HDDOT cap onto the participant's head, following a fixed series of steps to maintain consistency in data collection across subjects and scan operators. As indicated by these arrows, there are many degrees of freedom or for error depending on the position of the cap placement. So ensuring a consistent fit is very important. Then we use the subject-specific anatomy or a standard atlas to generate a head mesh, which we then use to simulate the position of the optode array onto the participant's head. Then we construct a light model to estimate the trajectory in which the light takes while exposed to the surface of the head and make our statistical predictions of brain function. In the next slide, I'm showing some examples of functional brain maps for individuals where they're doing the retinotopy task, where they're viewing a flashing checkerboard which appears either on the left visual field or the right side of the visual field. So this is unthresholded beta map from a single participant for a single trial, which included a stimulus on the left and also on the right. So this is the map that you see, and as with functional retinotopy maps, we can see the contralateral hemisphere being activated. Now, same thing with a single run. So this included 6 trials each for the left and the right. And now moving on to a single session where there were 2 different runs, a total of 16 minutes with 12 trials each. So as you can see, the localization of activity is improving as I increase the duration of my trials, the number of trials. And now finally, from a single subject data, for 96 minutes of this particular task, I'm able to localize the brain activity for this task in a very precise manner. So again, this is a graphic here showing the fidelity of my maps increasing as I increase the duration of data in my scans. So this is again the same map from that subject, and I have collected data from 4 other subjects. So you can see all of these maps mapped onto the structural anatomy of the individual subjects, and you do see the variability across activation patterns across all of these subjects. And I've also done that across other tasks with auditory, language, and motor. So with the auditory task, they were listening to a list of words. For the language task, they would see a noun on the screen, and the task was to generate a verb associated with the word. And for the motor task, this particular map is for the tongue movement task, where whenever they see the letter T on the screen, they would have to move their tongue to the left or the right side. So this is all the data that I have for my project at the moment. And all of these maps are generated from the data, for the duration of data I have shown in the chart on the left. So coming back to this idea of scanning people across multiple sessions, unlike fMRI, where you do have the anatomy of the brain available for you, in DOT, that one caveat is that we don't have the anatomy to go along with the functional activation. So it does take a little bit of positioning our optode array to where we think the optode array was during data collection and then doing our analysis. So on a good day, this cluster that you see indicated by the circles are centroids of activations from these different sessions. But purposefully, when we lowered the cap for these 2 sessions, we can see that the functional activation is lower, so which we know is incorrect, but could give us a wrong indication of functional activity in the brain. So we need to ensure that we are confident on our ability to place our caps in an appropriate manner. So to correct for it, we can rely on functional alignment as well. So again, I'm showing the results from the previous slide on here. This is session number 10, where we know that the cap was placed lower than needed, and the centroids of activations indicated by the lower circles. And what we need to do now is transform our array so that we match it close to the mean of our cluster of activations, which we are more confident about. And then after we do that, here is our activation. And another approach is to use photogrammetric alignment. So this step involves looking at photographs that we take during data collection. And conveniently with DOT, what we do see is there are impressions of the optodes that we can physically see on the participant's scalp that can be used as reference locations for where the optode array was during data collection. We can then use these photographs, overlaid photographs, to estimate positions and make our corrections and determine our array transformations accordingly. So this is just a pipeline showing some improvements in the positioning that we can do based on this method. So overall, this is where the functional alignment and photogrammetric alignment fits in the big data analysis pipeline. And these are all the progress that we're making towards forming a big pipeline to help with precision functional mapping in DOT. So this tool is essential for all of our projects. Like I mentioned earlier, imaging children during movie viewing, imaging individuals with cochlear implants, imaging during a face-to-face conversation, or even imaging while walking. All of these data collection efforts rely on precise placement of cap during data collection. So I hope that this project will lead into better data quality for all of these projects. And to conclude, we demonstrate the feasibility of using HD-DOT to carry out precision functional mapping in a single subject level. Alignment of data across multiple sessions is essential to yield high-fidelity results, and this improvement in functional and photographic alignment-based techniques will help reach its full potential. And the big picture being accurate single-subject mapping is an essential feature that can inform changes in functional brain activity over time. So this valuable resource can help us understand individual differences in brain organization. So with that, this is all the papers and projects from our group that are there at this conference. Please do check them out. And with that, I'd like to thank everybody for your attention.